One of the things that we realized that we could definitely make a use of is doing any sort of like data collection for research. Because a lot of these vessels that go out there are normally engine powered, so they make a ton of noise, or they're manned, which means they have to come back to shore for restocking purposes. And for that reason, we can actually have this vessel out and about for long periods of time. They don't require to come back and be refueled or anything like that. So that's what we took this shift. So we started this in 2023, right after the end of the RAY project. And yeah, the main focus again being to collect oceanic atmospheric data in the Pacific Ocean, and more particularly in the Gulf of Alaska. So we did a bunch of discussions with researchers, and they basically mentioned that that was a under-researched area, and so we wanted to focus on that because, again, just a bit difficult to get out there with regular means. And yeah, so going from there, we'll talk a little bit about the design of the craft, specifically the mechanical, electrical, and software systems, which are kind of our main pillars of the vessel itself. So we'll start off with the mechanical design. So one of the other big changes that we made with this compared to the previous ones is we switched to a rigid wing sail compared to a cloth wing sail, which I'll get into in a little bit here. But yeah, you can see there it's about 3 meters in length. The sail itself is also about 3 meters, 2.9 meters, with it, from keel to tip of the rigid wing sail there being almost 5 meters. So it's a fairly sizable boat. A bit of a smaller one from Ray. For context, Ray was about 5 meters in length. So it downsized it a bit, mostly just for transportation logistical issues, but still quite a large vessel to allow us to do all of our mounting of our sensors and things like that. Besides that, it's a fairly typical sailboat as you'd expect. It's got a keel, so the keel obviously prevents it from tipping over, especially with the rigid wing sail, because it's, catches a lot of wind and it has a high likelihood of tipping over. Our design philosophy with this was to make it as robust as possible. It's designed to go at about 3 knots in speed. That's the hull speed design. So fairly slow, but it is able to do like a full barrel roll and capsize and be completely fine. With that keel, it is self-righting, which is obviously very important. So we've got the rudder there, and then I'll talk about how the rigid wing sail works in a little bit. But on the right side, you can see the internals of the wing sail, which are just some CNC'd wooden ribs. And then we've got the leading edge, which is carbon fiber, which we'll see in a little bit as well. And then the exterior, which is really interesting, is actually fully solar panels, which I'll talk about in a second here as well. But diving into the hull, probably the most typical and standard part so far. It's just a displacement hull, fully carbon fiber. And yeah, we've just got a marine plywood interior and then carbon fiber sandwich on the outside there. In terms of what we've got going on the exterior, we've just got those black things that you see there, those circles. Those are just hatch hole covers that allow us access to the interior, which is where all of our electronics are stored. And then we've also got the solar panels, so one on either side, which you can see on the top-down view in the middle there. And then in terms of how we kind of came up with the design, basically just looking at existing literature and just trying to design something that has a larger volume interior, which obviously leads itself to being a displacement hull, mostly for giving us space for all of our electronics, and just to make it robust and stable, be able to handle the waves out in the Pacific Ocean. Getting into the sail, so as I said, this is one of the more unique designs with this iteration of our fully autonomous sailboat. So the exterior is fully custom solar panels. So we worked with a company called Open Water Solar, which is local to BC, and they actually design flexible fiberglass composite solar panels. So they basically take the cells and they sandwich them in a fiberglass composite, which makes them quite structural, and they're also flexible, which makes them really useful for our use case because we need to kind of shape them to be the exterior skin of our wing sail. So not only are they providing power for us, but they're also providing the exterior structural component, with the interior ribs providing any collapsing forces to be mitigated. In terms of the design of the rigid wing sail, it basically works like an airplane wing that you turn on the right side up 90 degrees. It works exactly the same otherwise. You can see the trim tab, which is that other foil that you see sticking out of it. So the interesting design with this is that The main large wing sail is actually fully free rotating, so it works basically the equivalent of a weather vane, if you can think about that. It will always align itself into the wind as long as the trim tab, which is that smaller foil on the outside, is set to the 0 angle of attack, meaning it's fully in line with the main wing sail. If you change that angle of attack of that smaller trim tab, then you can actually generate your thrust by adjusting the angle of the main wing sail with respect to the wind to actually generate meaningful thrust in the direction that you're desiring. And then that little thing on the left side that you can see is just a counterweight, and that's just kind of counteracting the moment arm that's caused by having that trim tab sticking out of the side there. And the video already played there, but that video was just us doing some testing of the flow over the wing sail in a wind tunnel. Moving into the electrical design, so again, a lot of learning that we had, especially from the Ray project, with some of the larger issues that we kind of ran into were specifically with the electrical design. So we really took a much deeper look into how we wanted to approach this, moving into a more modular design and focusing on off-the-shelf components, just making our lives easier. Don't want to reinvent the wheel, of course. And the main thing that we were focusing on here was the integration of the data sensors. Again, the entire heart of this project is to be able to provide a platformer for researchers to actually just very easily integrate any sensors, any research sensors that they want to be testing out, and be able to search them out quickly and just collect data as we go on excursions, bring it back, extract the data, and then send it out again. So getting into the overall system overview, this is obviously quite complicated, so I'm going to break this down very simply. So as I already mentioned, we've got the solar panels, so we've got 2 on either side of the wing sail and then 2 on either side of the hull. And that has to be stored somewhere, so we've got our battery system. And from there, we're powering our mainframe. So the mainframe does all of the computation for all of the autonomous sailing, which I'll talk about in the next slide. But basically it's doing all of that, and then also dealing with all of the incoming data, not only the telemetry data, but of course the scientific data sensors that are inputting as well. And from there, it's sending commands to the 2 actuation systems, which are our sail and the rudder. So again, with the sail, we're not actually physically rotating the mainsail. We're only rotating that smaller trim tab, which saves us a ton of energy, so making it a lot more power efficient. And then we've got the rudder at the bottom, which is also a pretty small motor. So that just makes the entire thing very energy efficient. And then, of course, as I mentioned, the heart of the entire project is the sensors. And again, this includes both the telemetry sensors, which serve as the eyes and ears of the boat, as well as the research data sensors as well. So kind of picking up from those sensors, they're kind of providing all of the inputs to the autonomous portion of the boat. We kind of transfer all of that electrical signaling into software signaling. So those get transferred to our networking node. And from there, it runs a pathfinding algorithm, which I'll talk about in the next slide. But basically, all that's doing is trying to figure out what the given waypoint that we've given it, how do I go from where I am currently to that specific waypoint. From there, it feeds into our controller. So this is what's actually sending the commands to our actuation systems. So what this is doing is taking a look at what is the current position of the rudder and the trim tab, and how do those need to be changed to make the actual changes to find the path find. So basically, what angle do I need to set the rudder to? What angle do I need to set the trim tab to actually move to the desired position? So from there, we again do a little conversion from the software side to the electrical side, and actually send electrical signals to the actuators. And another few things that the networking node can do is actually send external signals to the website. So we do this via satellite. So what that's actually sending over is like basic things like, what the battery voltage is looking like, where is the boat it's at this time, what's the speed, things like that. And that will actually be publicly available to everyone. So we're actually going to have this website live and running once we do excursions, which are starting at the end of August. So that'll be showing, again, like the position of the boat, how fast it's going, what is the battery, what is it doing, things like that, not only for ourselves, but also for the public. And from there, anyone can also download all of the research data that we're collecting, and also, just basically follow along for the journey. And then we're also able to input things over satellite as well, using our global path host. So what that basically means is that we're able to set high-level waypoints. So if we want to change where the boat is going, we're able to do that. Or if we want to tell it to come home, we can do that as well. And then another piece of learning that we had from our previous project that we really got hung up on was basically we weren't able to test our software system without having the electrical system set up first. So to give ourselves the ability to parallel process both projects, we ended up building a simulator. So this allowed us to emulate both the inputs from the sensors and the outputs to the actuators, and that way we were able to test the full software system without having the electrical system present. And again, that allowed both of those projects to run simultaneously. And the big question that we always get is how the heck do you tell a boat to sail autonomously? So as I mentioned, we have a bunch of telemetry data that we're collecting. So the main things being AIS, which is telling us where the boats are, basically, how big are they, what's their position, which direction are they moving, how fast are they moving. GPS, which tells us where we are relative to everything else. Wind, that obviously we need for our sailing, and then the goal location. So again, that's what we set with that goal path host. So the way that we end up doing this is using our GPS, we basically take a snapshot of the nearby area of the vessel. So the vessel is represented by that yellow dot at the bottom there. And we basically set up a grid. So we basically have a bunch of points. This is not exactly to scale. Obviously, it's much more fine than this. But just to give an illustrative example, this is kind of what it would look like. And what we do is we first begin by removing all of the dangerous waypoints. So the way we determine those are anywhere there's vessels. So we would make basically a bounding box around that vessel based on the size of it. And again, the direction that it's moving and how fast it's moving. So we know that those are areas that we don't want to move the boat into. And then, of course, any sort of land masses would also be areas that we don't want to approach. And then with the remaining waypoints that we have, we actually take the boat and we just move through those remaining waypoints with the shortest path. So for anyone who's familiar with any sort of CS algorithms, all we're doing really is just trying to find the shortest path possible with the lowest cost. So we have a few different parameters in there as well, some of them including how many actuations we have to do. So again, being wary of how much power we're drawing. So sometimes we might not take quote unquote the shortest path, but it might require fewer actuations and just make more sense. So there's a little bit more refinement there, but generally all we're doing is calculating the shortest path possible. And that basically takes this very complicated problem and breaks it down to just calculating the lowest cost path. Getting into the manufacturing, so after our year of design in fall of 2024, we started actually designing the whole thing. So you can see our initial small prototype at the top left where we were just kind of validating our composites workflow. In the top middle there, you can see the initial internal shell that is of the marine plywood that we've got held together. And then on the right there, you can see us laying down our first layer of carbon fiber just through wet layup. Bottom left, you can see us doing vacuum bag, and at the bottom that just finished, that was a time lapse of us doing a full day of work on the vessel itself. And on the bottom right, you can see us getting pretty far there, having cut in some hatch hole covers that I mentioned earlier. Getting into the spring, which is our following term, that was basically taking, now that we had the initial shell, now we were just kind of working on doing some fairing, doing the painting, basically post-processing of the entire composites workflow. You can see the wing sail coming together there. So the leading edge got completed this time. So that's that black front that you see there. And you can see the CNC'd ribs coming together there as well. At the bottom left, that's the CNC'd keel. So that's the internal keel that was, again, faired and painted as well. And then at the bottom, there at the bottom right, you can see the rudder coming together as well. In the summer, we actually had the complete vessel completed. So you can see us unveiling it to the public for the first time at OME last year. You can see some lead casting happening. That was the kind of last bit that we completed, which was that counterweight that I mentioned for the trim tab. And then you can just see the completed sail as well. So we've got the solar panels cut to size and bolted to the shell. From there, we were able to do our first launch, so that was completed at the end of August of 2025. So you can see us getting the boat into the water. Since then, we've done a number of on-water tests out of English Bay, and we're continuing to do those this summer as well as we kind of finalize all of the systems integration and validate all of our testing. So yeah, you can see us doing some CLR testing there at the top right. And from there, we are also able to collect our first data sets for research data collection. So we're working with a bunch of really cool folks. So initially, it was kind of difficult to start pitching this project because we obviously didn't have anything physical to show them. But as we've kind of started to developed this project, now that we've been able to put it out to the water and actually collect data, we've actually started to get researchers reaching out to us, which is really cool, of course. So yeah, our initial kind of folks that we're working with some hydrophone data. So we're trying to work with the Orca Behavior Institute because basically the current situation they're working with is they're trying to track southern resident killer whales in the Pacific Ocean. And the way they do that is they have stationary buoys with hydrophones attached to them, and they're basically relying on these pods to go nearby these buoys, and they're able to pick up on sound signatures and figure out how many of them there are and things like that. But of course, those are stationary, and that's again, where this unique use case comes in is that we're able to stay out in the water for long periods of time. It's self-sustaining. And another thing is it doesn't produce a bunch of noise because it doesn't have any engine on board. So it really puts us in a good position to be able to assist with that. So we're working with them to get everything working with the hydrophone. And then we're also collecting particulate matter data with Dr. Naomi Zimmerman here at UBC. So her research focuses on basically monitoring air quality. They have this plume van that they drive around UBC, and they basically figure out concentrations of various particulate matter and how that varies over time. And so what we're able to do is kind of extend that research out into English Bay and beyond, rather than just on land. And beyond that, we're also collecting water pH, salinity, and temperature. And those are all just great metrics to have as like a basis of kind of what's going on in the Pacific Ocean. Beyond this, we're also working with Dr. Philippe Tortel recently, so another professor here at UBC, and they're working on a self-calibrating oxygen sensor that we're hoping to integrate into our vessel as well within hopefully the next year. So again, looking forward at what's next. So just a bunch of implementation that we're wrapping up and doing integration testing and validating our systems. And we're hoping to have this maiden voyage in August from Banfield Marine Science Center. So we're booked in there, I believe, from August 18th to 22nd. So if anyone here is going to be there, please do come say hi. I believe there's some sort of event happening there as well, so some folks might be there. But yeah, that's our next step there, is just getting everything up and running, and we'll be there at the end of August to do a multi-day launch. Thank you so much for bearing with me here. Really appreciate it, and I believe there should be some question time, so I'll leave it open to the floor.
Thank you very much, Pawan. Really interesting, especially for those engineers, naval architects, data nerds. Love the detail, love the story, so congratulations. Looks like we have our first question from Doug Beckett. Go ahead, Doug.
So I'm familiar with open water solar, and their solar panels are amazing, possibly the best in the world. I guess if you're going to space, it might be different, but that's a bit of a different class. How did you luck into open water solar? Was that by design or what?
No, absolutely fantastic question. It's quite interesting because we were trying to maximize the input solar power that we could get. And so we kind of came to this design that it would be awesome to have solar power coming in from the wing sail as well, because it's such a large surface area. And so we were kind of just trying to look around and see, if there's any way to do it. And the existing solutions, of course, are all rigid panels. So that basically limits you to the flat area that you can get, which isn't a lot. So you can see it's a very angular design for that reason, is to kind of, when we first started designing, we didn't have open water solar in mind at all. And so we were trying to make as much surface area flat and rigid as possible so that we could accommodate as many solar panels. But then we ended up stumbling across open water solar, ended up sending out an email, and they were super ecstatic to test out their technology with this vessel, because it's kind of like the exact use case that they're really pitching. As the marine landscape is what they're interested in, and specifically with this being the only thing that we could use really is flexible panels to get maximum coverage on this wing sail. And so they were super happy to accommodate this, and they worked with us very closely to get the design up and running and maximize the solar cell count that we could get on this wing sail. And yeah, from there we were just able to get them shipped over, and we were able to cut them to size and fit them onto the wing sail.
And a product that all vessels that are involved with shipping should keep in mind, because they can make them so they're rough surface, a grip surface, but they still produce very durable. And the transport sector, they can give you a license to produce solar panels for reefer units to run the refrigeration units, even on diesel vehicles, but even better with the electric. So good. Thank you.
Yeah, thank you.
Okay, Craig Summers, go ahead.
Hi, Pawan. I just wanted to show you the wind sensor that SailTimer has, which uses the same principle as you. Our direction finder to catch the wind has a solar panel in it, so it's and a counterbalance. So it's miniature design, but sort of similar to yours. But I had a question for you about your trim tab. I don't know if you know of the company called Sail Drone in San Francisco. And I think the founder there was the one who came up with that whole idea. And I would have thought, because they are pretty aggressive in terms of venture capital and intellectual property, that they probably have patented that. But have you looked into that issue? I haven't seen anyone else use that design.
Yeah, no, absolutely. No, it's a very good point. Yeah, we did try to reach out to them for this exact question, and I don't recall us getting any answer back. For context, they started off pretty quote unquote open source, if you will, and they were doing a bunch of cool research, and then moved into kind of defense contracting. So it's I think they're working with the U.S. Navy at the moment. So things, I think right when we started reaching out was when they kind of closed their doors, if you will, to the public. So I don't think we ended up getting any answer from them. But generally, the result with us is that since this is fully research focused and it's a student team, there's like zero profit that we can make from this. So that kind of absolves us from that issue, is that we're not trying to make money off of it in any way. And I think actually recently we were at Miratech last week, and I actually ended up getting into contact with a company that actually works directly with SailDrone, and they mentioned that they might be able to connect us. So I'd actually love to chat with the folks there and see what they think of this entire project. But yeah, definitely a great question.
Interesting. Thank you for the presentation. It was really interesting.
Thank you.
So Pawan, I have a question for you then. You said you're not planning to earn a profit, or sounds like commercialize. I was watching the presentation thinking that maybe this is the beginning of a startup. You get into the creative destruction lab, accelerate your business, learn how to attract venture capital, and you're off to the races. Is that not your plan?
Unfortunately not. So for a number of reasons. The main reason being that it's a student design team, so that actually like legally binds us from ever making a profit. So within UBC, there's a bunch of very strict regulations for that, and any student design team can't spin up any sort of startup or anything like that from any projects that they work on here. So for that reason, yeah, there's like no chance of that happening. So yeah. Okay.
We have a question from Robin Stapleton.
Yeah, great presentation, great project. Amazing to see what you guys are doing. Can you talk at all about like the regulatory requirements around an autonomous vessel and how you comply with call regs?
Yeah, no, absolutely. Another fantastic question. So when we first started back in 2014, there was no existing regulation at all. Since then, actually kind of they're in between like Ray and our previous project and Polaris. Our current project is kind of when MAST came into effect. So for context, that's a full bill that's passed from Transport Canada that kind of oversees any maritime autonomous sailing vessels. So the context with that is that this vessel, when we started designing it, we weren't aware of it. I don't even think MAST had come into effect like when we first started designing this vessel. So we didn't actually consider any of the MAST regulation at that time. So this isn't actually really designed to be compliant with that. And so our workaround, if you will, for the time being, while we kind of figure that out, is to tow Polaris out 10 or 12 nautical miles out from the coast to get it out of Canadian waters where MAST does not apply anymore. So it's a bit of a workaround for sure, but it's a student design team, so it's kind of how those things work, I guess.
Thank you.
Yeah, absolutely.
Are there any other questions? So I'll ask another one. So by high level, pardon the pun, how does this compare with, competing against satellite data? What are you collecting that satellites cannot collect?
Yeah, no, fantastic question. Yeah, so I mean, with satellites, like what we're trying to focus on is anything that we can connect locally. So like things like the water pH, salinity, temperature, you kind of need
Mhm.
something, in the water itself. And then the main thing that I was kind of touching on as well is the fact that you can move this around. So there's a ton of, sensor arrays that you can put up with buoys or, other kind of stationary items that, again, you can kind of ping to satellite and, you can set it home and monitor that. But the biggest thing that we're focusing on is being able to allow it to move around and send it to specific points and make it really modular. So just basically like the quickest way that researchers can kind of get their data sensors on board and be able to collect data and extract data and really customize those voyages to what they need. If they wanted to kind of circle around in some area, we can do that. If they want to send it to a specific point, we can do that as well. Kind of really the sky's the limit in terms of what their interest is and what they're trying to do.
Okay, and another question. Oh, go ahead, Robin.
Yeah, I was just curious about that. What
Yes.
kind of power budget you have for sensors?
Yeah, fantastic question. Yeah, actually, I didn't put an appendix in this one, but we do have a full power budget as well. But that was the entire intention of trying to maximize the solar panel surface area. So we've got a pretty large battery on board as well. So basically, the calculation that we did with all the data sensors that we currently have spec'd, so that includes like the pH, salinity, water temperature, all of that, and then the hydrophone and the PM data sensor as well. With that, we're able to run 5 days continuously without any solar input whatsoever, so just with the battery pack itself. So considering that we're starting off by launching during the summer, Alaska's got pretty good, up in there, Gulf of Alaska, it's got pretty good solar coverage. So within the summer, it should be pretty solid. I would be very surprised if we're not seeing any solar input whatsoever for 5 full days. So hopefully it's pretty much self-sustaining as it is, but yeah, that's kind of the numbers.
Great, thanks.
Have you thought or any plans to track emissions data, methane or other kinds of carbon emissions?
Yeah, that's a great point. Not at the moment. So again, like the main, I guess for further context, the 3 main sensors that we started with when we first designed this was just the water pH, salinity, and temperature. And since then we've added the hydrophone and the PM data, and then now we're also working on that oxygen sensor as well. But yeah, hopefully we can get into contact with someone who's within that field and would be interested in this this design and would want to add their sensors as well.
Go ahead, Craig Summers.
Pawan, since we see a little bit of extra time and maybe not a lot of competition for questions, I'll torture you with a trickier question that maybe you have a more detailed answer for than you gave in the presentation. With the weather routing that you do the autonomous route calculations for, you said the main goal is to find the shortest path possible. But when the boat is going upwind, the shortest path possible gives you no power because it's straight into the wind. Therefore, you must have some other tacking algorithm that you use.
Yep. No, fantastic question. Yeah. Yeah, no, that's I just didn't mention it again just for the presentation. But yeah, the other thing, because we have wind data, we are able to figure out if we're going upwind, downwind, things like that, and we will adjust like either tacking or jibing based on that. So yeah, we won't just try to send it fully upwind or anything. In terms of, I guess, further context as well, at the moment, we don't have any sort of long-term forecasting of weather. So this is a common question that we get, especially given our previous experience with Eta and, hitting 3 hurricanes. We don't have any sort of long-term forecasting at the moment. The way that we're getting around that is basically monitoring it on land and being able to update those global waypoints if we need to. So if we, see that there's something coming, we can either, bring it back home or, adjust the path and things like that. That is something that we would be interested in. So, either like inputting some sort of data from like windy.com or, some other weather system that we could, easily integrate. But at the moment, as I explained it, this is like all happening locally, on boat. And that doesn't get any sort of input data of the external weather other than what it's just seeing there from the wind and things like that. but definitely something I would be interested in the future.
I could add one follow-up question to that. Incidentally, our company, the address, the website is sailtimer.co, and we do have crowdsourced weather maps, which are similar to Windy, but Windy only uses satellite weather for the wind, which is inaccurate and low resolution. So you may find some advantages to using crowdsourced wind data, which SailTimer has. But I was curious, in order to calculate your routes, then, do you have polar plots for the boat, or are you familiar with polar plots as a sailing technique?
A little bit, yeah.
And do you use those, or that would be a helpful algorithm, and that's kind of the next step. You didn't mention it yet, but to make more sophisticated routing calculations, polar plots are the standard way to do it.
Yeah, no, exactly. Yeah, no, nothing like that at the moment. As I mentioned, it's basically what it's doing is taking a snapshot, setting up a grid, and that's pretty much it. Nothing with polar plots at the moment. But again, I think that would be the next step for us, is to get, weather integration and kind of bring it up from there. Yeah, exactly.
Great, thank you.
Okay, any other questions? Well, Pawan, that was a really interesting presentation. What a fantastic project. So congratulations. I should mention to everybody here that the Vancouver Maritime Centre for Climate has partnered with UBC and the Naval Architecture and Engineering team out at UBC to host an event. Should probably double check the date. I
think they
believe
mentioned
it's
September or October, yeah.
Yeah, September 16th. And during that time, we'll have a chance to do a site visit to see SailBot's lab. So for those of you that are interested, please continue to follow the VMCC, and we'll get that information about the entire event to you in the coming months. Next month, on June 16th, I think, or June 17th. On June 17th is our next webinar, and that'll be featuring VoltSafe. Many of you know VoltSafe is a Richmond-based company that designed the marine battery electric solutions for ocean-going vessels. Several years ago, they were acquired by a Norwegian company, but continue to have a pretty big footprint here in Richmond. So we'll hear from them, get a progress update on how things are going with battery electric. So we hope to see you then. And until then, thanks so much for your support of the Vancouver Maritime Centre for Climate. Have a great day.
Thank you. Thank you so much for having me. Appreciate it.
You bet.
Take care. Bye.